All right, hello everyone. We're back in chapter 1, section 1.2, displaying quantitative data with graphs this time. Section 1.1, we looked at categorical. We are now looking at quantitative. So for learning targets, make and interpret dot plots, stem plots, and histograms of quantitative data. Identify the shape of a distribution. Describe the overall pattern, which is shape, center, and variability of a distribution. And then identify any major departures from the pattern, which we call outliers. Compare distributions of quantitative data using dot plots, stem plots, and histograms. So the first thing that we're going to use or the first graph we're going to create are dot plots. A dot plot shows each data value as a dot above the location on a number line. So how to make one? Draw your axis, a horizontal axis or a number line. Scale it with whatever your data is. So this data set, I think we're looking at the amount of goals the U.S. women's national team has scored. So that's why the scale is 0 to 10. And then you put a dot for each data value. So for example, this dot right here represents that in one game they scored 4 goals. This dot means one game they scored 5, another game of 5, and another game of 5. So each dot is its own data point. Some good things about dot plots. Well, one, we use it pretty often, if not one of the most often ways to show quantitative data. The other thing too is it's pretty good for it can be used for small or large data. To do it by hand, it's really nice for small data because you just draw your number line and put a dot or an X on each spot. But to make it by hand, if you had like 150 data points, it's kind of a lot to plug in each one of those data values or plot each one of those points. So we could use computer algorithms or some computer outputs to help us with it. But if it's a small data set, it's not too bad to make it by hand, but it is probably one of our most common graphs that we use. The reason dot plots are nice is because they help us describe shape really easily. So we have a couple words to describe shape. So the first one's going to be roughly symmetric. A distribution is roughly symmetric if the right side of the graph is approximately a mirror image of the left. So here you can see that kind of if I split this graph in half and I like fold it over, they're pretty much symmetric. There's 2 and 2, 3 and 4, and 5 and 6. So it's pretty symmetric here. And so that's why we say we say roughly symmetric because it's not guaranteed to be exactly symmetric. So use that roughly just to kind of cover our basis there. This is where I said like our language is really important in this chapter now. Well, in this whole class, but saying symmetric and roughly symmetric are not the same. If I say something symmetric, then boom, it's perfectly symmetric. But to get around that, we say it's roughly, and that kind of does it for us. The next one is called skewed right, and it's skewed right if the right side of the graph is much longer than the left-hand side. So I think the easiest way to do this is if you see my mouse, if I kind of draw over this graph and come back down, kind of looks like that bell-shaped curve or that normal curve a little bit. That's what a symmetric graph is going to usually look like. A skewed right is when I come up, boom, and then I flatten out and I have this super long tail. Okay, so the skewedness is wherever that long tail is. So I come up and then boom, I have this long tail. All right, so there's a little bit of data on the right, and that's the direction of the skewness. So for skewed left, I have this long tail, and I come and get most of my data. So skewed left is where there's a little bit of data on that left-hand side. It's a lot more spread out. You can see with these kind of, where they're showing about half of the data. See how much longer it takes to get half the data on a skewed left than on the skewed right. Versus the symmetric, about both are half and half. And they're about equal distances for half and half. So just a caution, obviously the direction of skewness is towards the long tail, not the direction where the most observations are clustered. Another word we use is so not just direction, that was part of the shape was the direction. Symmetric, left skewed or right skewed. Then we have unimodal, which just means it has a single peak. So there's a big cluster here. So it's a unimodal graph. This would be a bimodal. There's two peaks, right? If I kind of draw a line around the data, two big peaks. So this would be bimodal. And I want to say for this one, this is actually a typo. Let me fix it here. I feel like this is not supposed to say approximately symmetric, but it should be unimodal, bimodal, uniform. Sorry. So a uniform distribution is kind of everything's about equal. It's uniforms, right? Think about like a sports team. If you're in uniform, everyone looks the same. So same thing here. All the data values look about the same. They all have roughly the same number of data values for each. So that's uniform. So that was all about describing the shape. So you want to say the direction, and you also want to say like unimodal, bimodal, or um, uniform, and that's based kind of on the peak of the graph or if there's any clusters. You can also say if there's any gaps there, and we'll go more into this, but let's go back. So like here, if I wanted to describe this shape, right, I'd say it's skewed right because the long tail to the right. It's unimodal with a cluster around 1 and 2, and then there's a gap between 5 and 9. So there's a gap here between these data values. So there's nothing there. So it's not a bad idea to include gap, clusters, peaks, and then direction. All right, so that was just describing the shape, but we do have to describe the distribution as a whole. So there's four things we look for when we're describing the distribution. Um, so you can describe the overall pattern by its shape, which we talked about, the center, and the variability. And then the fourth thing, which is important, is the outlier. Okay, so the outlier is anything where like a data value just doesn't seem to fit. Maybe it's a departure from all the other observations. Right. The shape we talked about, the center is just where the center of the data is, and the variability is how spread out that data is, or how much it varies from that center. When you are talking about it, so if on an AP question, it's not uncommon to be like, hey, describe this distribution. So you need to hit those four things, and you also need to describe it in context. What does context mean? Just put it back in time in terms of that problem. So about the number of goals scored, you would say the distribution of women's national team goals scored is skewed right, with a center as being the mean number of goals scored was 4 or something like that. You see, I keep bringing up whatever the variable is we're talking about. That's how you put this in context. So using variable names, not just the units, not just goals scored, but for what? The U.S. men's national team games who scored 4 goals or something along those lines. So let's go ahead and describe this distribution. So like I said, this is 20 games played in 2016 U.S. women's soccer team. So the shape, the distribution of goals scored is skewed to the right with a single peak at 1 goal, and there's a gap between 5 and 9 goals. So um, distribution of goals scored, so that's the context. We got the direction skewed right, a single peak, and then a gap as well. Outliers. The games where the team scored 9 and 10 goals appear to be outliers because they're pretty far away from the rest of the cluster of data points. So they seem to diverge from the rest of the data. The center, the median is 2 goals scored. We'll talk more about the how to calculate center. There's a couple different things you can use for center. And then variability, the number of goals varies from 1 to 10 goals. And we'll also talk about a couple different ways to calculate variability and give you some other um, names you can use. But it does just vary from 1 to 10 right now. And you see how each one has goal scored, goal scored. Um, the team scored 9 goals. They're always putting in context. Yep, and there's everywhere where they talk about the context. All right, so that was describing one distribution. Sometimes you'll be asked to compare distributions. This is not uncommon. Probably the most common would be like describing a distribution for male and female, maybe between two schools. So if we want to compare like north or central countries, it's very common to compare distributions to see, hey, are things similar? Are things different between two groups of people? So we use census at school's random data selector to choose 50 students from each country. Here are dot plots of the household sizes um, reported by the survey respondents. Compare the distribution of household size for the two countries. So there's the data. So let's go ahead and compare. When comparing distributions for quantitative data, it's not just enough to list the value of center variability. You must explicitly compare them using words like greater than, less than, or about the same. So I would set this up the same exact way as before. I'd do shape, center, variability, outliers, and then in the shape, I'd say, hey, the South African shape is skewed right, while the UK is approximately symmetric. And so you get that comparative right in there. And then when you do compare like numbers wise, you want to use greater than or less than or about the same. You want to use those ER words to really drive home um, the comparison between the two distributions. So here we go. Shape. The distribution of household size for the UK sample is roughly symmetric with a single peak at 4 people, right? So direction symmetric, and then that unimodal at 4 people. The distribution of household size for South Africa sample is skewed to the right with a single peak at 4 people and a clear gap between 15 and 26. So you get that gap in because there's a gap. There's no gap for the UK, so you don't have to mention anything like that. For outliers, there does not appear to be outliers in the UK distribution. The South African distribution seems to have two outliers, the households with 15 and 26. Now, if you didn't say 15, I think you'd be okay here because it's kind of close to that 12, but 26 is certainly an outlier. Center, the household size for South African students tends to be larger. So you get that ER word, the median of 6 people, than the UK students were a median of 4 people. So you get that ER word is larger for South African than UK. And then variability, household size from South Africa students vary more from 3 to 26 people than the UK from 2 to 6 people. So again, get that very more. So you're directly comparing these. And obviously we use context talking about household size quite a bit and that comparative language. All right, another stem plot, or sorry, another graph we could use instead of a dot plot is a stem plot or a stem and leaf plot. So the stem plot shows each data value separated into two parts, a stem which consists of all but the final digit and a leaf, the final digit. The stems are ordered from lowest to highest and arranged in a vertical column. The leaves are arranged in increasing order out from the appropriate stems. I think just showing a diagram will be a lot easier than kind of explaining it. So here's the data. So we're going to make a stem and leaf plot. So we make our stems, right? Our stems are, so it's really, our leaves are the last digit. So here's the two, these are all 2 digits. So our stems are going to be the tens place. Our leaves are going to be the ones place. So we look at the stems, we got data anywhere from 1 to 50 is our largest one. We make our stems. Then you add the leaves in. So like 50 would be 5, 0, 26, 2, 6, 26, 2, 6, 31, 31, 57. You add that 7 there. 19 out of 9. And then once you have all of it, now you order the leaves. So now these are all in ascending order. And then you have to add a key. This was just on the AP test. There's one with this. And if you don't add a key, you automatically lose points. So the key is just you pick any number you want. So like, hey, this is 4, line 9, represents a female student who reported having 49 pairs of shoes. Yeah. So when there's a lot of data or it's all bunched up, we can split the stems and kind of make the data a little bit easier to see. And you can also use two distributions to make it back. So let's do that. First, we're splitting the stems. So instead of having 0, 1, 2, 3, 4, 5, we have 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. So this first one is going to hold the numbers 0 through 5, and then the next one is 6 through 9, or 0 through 4. 0 through 4, and then 5 through 9. So you can see here, this 0, 4 represents 4 males. This 1, 0 would be 10, and it's for males. So same thing, it's just instead of having it all in one, instead of having like these, I don't, it just breaks it up a little bit more. So instead of having like 5 stems at one, it gets broken down to 3 and 2. A back-to-back stem and leaf plot is exactly what it sounds like. You just have one set of data on the right-hand side. So imagine if you kind of covered this up here, it would look just like a regular stem plot, stem and leaves. But now you're going to compare it. So you have the two data. So these are for males, the females on this side, and it kind of gets mirrored over. So now you go from smallest to largest out. So 5 to 9, 2, 3, 3, 4, 6, 6. So imagine if like you flipped it over, it would be going from smallest to largest, right? And of course, you still have that key. So that's it for stem plots. Stem plots not super common. They take a while if you have a lot of data points, um, but um, yeah, they take a while, but they can be useful because you kind of start to see the shape a little bit of the two distributions. Um, it's just turned 90 degrees, so like boom, this would be like skewed right, and this looks kind of more symmetric, if not, yeah, maybe more symmetric or uniform, depending on it. It's not the best for seeing shape, but at least it gets you an idea of what you're thinking of. Um, but yeah, they're not super useful because they're super big. Kids often forget to put a key in there. So that's an easy way to lose points. And then also the other big mistake is people omit stems. So like for this case, like this 4 doesn't have anything. A lot of times people just delete it. But the problem with that is now you've kind of changed the scale of this graph. It would be like if in that U.S. soccer when you just didn't include 6, 7, and 8, and you just put the 9 goals right next to the 5 goals. Well, now you're missing that gap. So omitting stems makes you not see any gaps there might be. So that's a problem as well. So do not omit any stems. Just put every number in there. But I do think that it helps compare the two data pretty easily because they are right next to each other. Mhm. So the next thing is a histogram, and a histogram shows each interval of values as a bar. The height of the bar shows the frequencies or relative frequencies for each value in each interval. So here's our dot plot that we have turned into a histogram. So now you make your bars a certain width or an interval. So this would be like 1.5 to 1.75 and 1.75 to 2. And so any data that falls in 1.5 to 1.75, boom, those get into this bar and so forth. For intervals, you just want to make sure that they're pretty, um, they just make sense to the average person. So like in this case, you're going from 1.5 to 5. So a bar or like a width of 2 is just too big. Like that doesn't make sense because you'd only have like 2 or 3 bars. Um, so just pick an interval that makes kind of sense. Um, and this interval is a good interval because it still allows you to kind of see the shape. If your interval is too big, it's just going to start to look more and more uniform or symmetric. You're going to lose some of those shapes potentially. Um, the good thing about histograms is that you can put a lot of data in here very quickly because you can just count up how many fall into each category. Boom, make a bar. You don't have to make an individual dot each time. But the disadvantage is you do lose sight of that individual data value. Like for example, on this dot plot, boom, I can see, hey, there's 3 data points that are right here at maybe like 2.75. I don't see those exactly. I lose sight of the individual data value, but I can see the whole group a lot easier. Those are kind of the pros and cons to using a dot plot and a histogram. Dot plot, you see the individual data value, but maybe it's a little harder to see the whole group. or it takes a while because you could put a lot of dots onto a dot plot. So yeah. So how to make a histogram. Choose equal width intervals. That's a big thing. They do have to be equal width. Um, so we're going to go here. We're going to go class. I don't know. So we're going by fives. Make a table that shows the frequencies or relative frequencies. Um, so remember, frequencies would be like counts. Relative frequencies would be like a proportion or a percentage. Draw your horizontal and vertical axes and have to label them. So this is where it's important. If you choose like your frequencies, then it's number of states. If you choose percentage, then this would have to be percentages. Histograms would be either one, but you want to make sure that you are labeling it correctly and labeling the x value or the x-axis as well, which is whatever variable you're looking at. So you need to label it, or else, just like if you don't have your key, if you don't label your axes here, you're going to lose points. Same thing on a dot plot. If you don't label the axes, the x-axis, you're going to lose points. Scale the axes now, and then draw the bars above. The interval, the bar height corresponds to the frequency or relative frequency of that interval. Here's some cautions for you where a lot of people do make some mistakes. Don't confuse histograms and bar graphs. Histograms are for quantitative data and they are intervals. Bar graphs are for categorical and they are a category, or they are, yeah, they're not, it's not a interval, it's a category. So those are different. Use percentage proportions instead of counts on vertical axis when comparing distributions with different numbers of observations. We kind of talked about that in 1.1. It's not necessarily fair if one group has 50 people and the other has 300, and then you're saying you're going to use, oh, look at that, like 100 people voted for that other one. But there's just so many more people. So instead, when you're comparing it, it's better to compare the proportion or the percentage of the whole if the sizes are different. Right? And then just because a graph looks nice doesn't mean it's useful or helps data. Um, so just be aware of bad graphs. I think we'll probably take a look more in class about them. But yeah, just make sure that you know the difference between histograms and bar graphs. Right, and that is it for this video. So to finish up these learning targets, we were able to make and interpret dot plots, stem plots, and histograms for quantitative data. We identified the shape of a distribution, either symmetric, left skewed, right skewed, and then is it unimodal, bimodal, uniform, and then are there any gaps? We described the overall pattern, or when you describe a distribution, you need to hit shape, center, variability, and outliers, and you need to talk about the context along with it. And then when you compare distributions of quantitative data using dot plots, stem plots, and histograms. All right, thank you for watching.